Today is December 9, 2021, and I'm going to cover chapter 19. Today is a partial, that is the last partial exam. Next Thursday is going to be the final exam. Okay, so here you go. What you have to know about chapter 19? So far, up to now, we have been dealing with only three basic quantities: length, mass, and time. And it is at this point that we introduce a new basic quantity that we call the temperature. Okay, again, those four quantities are at the very core of physics. At the very core of physics, we have the basic quantities, we have the primary definitions, and we have the laws of physics. So far, you have seen three laws of physics: Newton's second law, Newton's third law, and law of universal gravitation. Newton's first law is not a law. Newton's first law is a consequence of the second law. So it's considered, strictly speaking, it is a corollary, a corollary to Newton's second law. Okay, so far three laws. Okay, and a new. Everybody's familiar with the concept of temperature, right? So and so there is this other idea. Okay, here you go. Let me see how I'm gonna do that. Yeah, there is this other concept of thermal equilibrium. Okay, and what's thermal equilibrium? Thermal equilibrium is whenever two objects do not exchange any type of energy between each other. Okay, any type of, let's say, thermal energy. If two objects have different temperatures, there will be an exchange of thermal energy through heat. Okay, if they are in contact with one another, in thermal contact with one another. If they are the same temperature, there will be no exchange of thermal energy. There will be no heat transferred. And that's an important difference between energy and heat. Okay, heat, here you go. Let me write that down here for you. Concept of temperature. U basic, how do we call it? Basic quantity, yeah. New basic quantity. New basic quantity. Temperature. Temperature, like I said, is at the very core of physics. You don't define temperature in terms of anything else. Just like the length, just like the mass, just like the time, you do not define any those with respect to anything else. They're by themselves. Okay, temperature. And there are ways to measure temperature. Let's put it this way here. Let's write that down here. There are different ways of measuring temperature. No, either by thermal expansion, by by the color of an object, by the color of an object, or by, here you go, by the it, by its electrical properties. Different ways. There are several ways to measure temperature by its electrical properties. Oh, even by the pressure of a gas. Pressure of a gas. You can use the pressure of a gas to measure the temperature of a gas. So, all sorts of different ways to measure temperature. We do know that the bluer an object is, the warmer it is. Okay, so, and then what else you have to know? you have to know about temperature scales. How we quantify temperature, okay? How we quantify temperature using scales. There are three important scales. Quantify temperature by using temperature scales. That is the Fahrenheit, that is the Celsius, and the most important of them is the Kelvin. That's the real SI unit. Any temperature should be expressed in terms of Kelvin. Although sometimes it's far more convenient to express them in Celsius or Fahrenheit than in Kelvin. Okay. Kelvin has the temperature, has this important property. Has this important property that's not obvious. That is not obvious. It's not obvious. Okay. You can go as high as you can. You can go as high as you can in temperature. What do I mean by that? There is no limit. There's no nature. Nature imposes no limit as to the highest temperature. However, nature does impose a limit in the lowest temperature value. That's what we call the absolute zero. The absolute zero. And that's where the Kelvin scale came from. Okay? The temperature 0 Kelvin is the lowest temperature you will ever find in physics. Okay, there is no such a thing. In other words, there is no such a thing as negative Kelvin, as a temperature that is negative Kelvin, as a negative Kelvin temperature. Can you remember that? It's possible to make experiments to determine how this temperature relates to the Fahrenheit and the Kelvins and the Celsius scale. It's possible to do that. Okay, so let me see if I have a slide here. Let's see. Oh yeah, here you go. Maybe I have a better slide. Yeah, let me check if I have a better slide here. Let's go on here. Oh no. Well, so yeah, I don't have it, so it's gonna be without the slide here. So 0 Kelvin means what? 0 Kelvin is represented by the letter K. You know, Celsius is represented by the degree C, the unit degree C. And 0 Kelvin is minus 273.4 C. Even I don't memorize those things, but it's something around that. Let's see. How is that? Uh,
Negative 273.15.
point what?
Point 15.
15, 1 5, okay.
Yeah.
270,
It's a
okay.
little bit higher.
Yeah.
Right there in the top right.
Oh, here you go. I got it. Thank you. Yep. 273.15. 273.15 degrees C. Okay. And there is a conversion between Celsius and Fahrenheit. We do not put degrees on Kelvin, but we do put degrees on Fahrenheit and Celsius. Okay, so how do you convert that Celsius to Fahrenheit, to Kelvin? We convert that by a very simple notation. Temperature in kelvins is going to be what? Temperature in C minus, no, it's not minus, it's plus 273.15. Okay, is that right? Yeah, at 0 degrees C, we have 273 Kelvin. It's a very simple conversion. What's not simple is converting from Celsius to Fahrenheit. So, and how do we define those scales? Okay, there's a way to define those scales. A definition that's stuck. You know, the idea of definitions has nothing to do. Definition of scales has nothing to do whether the scale is useful or not. It has to do is whatever the scientists choose. The Okay, so the Celsius is just like that. Okay, and the Fahrenheit. Let's take a look at the Fahrenheit. There's a relationship between Celsius and Fahrenheit. Is this relationship here? Okay, there is approximately 2 degrees, a factor of 2 for Fahrenheit. Okay, 9/5 is approximately 2. It's 1.8. 2 minus 10%. 2 minus 10% of 2. That's how you should look at that if you want to memorize it. So if you have, for instance, and then we have this correction here, this 32 degrees Fahrenheit. So if you're dealing with low temperatures, 50 degrees C, okay, 50 degrees C is going to be approximately 100 Fahrenheit plus 1 plus 32. It's going to be 132. Okay? Make sense? 50, no, right? I said 50. 50 times approximately 2 is 100. Actually, minus 10% is going to be 90. Should be 122. That's your rule of thumb way of calculating conversion of temperature. Okay, so for low temperature, you have to worry about this 32. But for high temperature, so let's say 1,000 degrees C. 1,000 degrees C, it's going to be much larger than this correction here, than this, let's say, this intercept, okay, value. So you're in very good shape if you just say that 1,000 degrees C corresponds to approximately 1,800 Fahrenheit. You're in good shape. The error is going to be very small because 32 is much smaller than what you got here. Make sense? Okay? We usually have those. It's usually good to have those rule of the thumb calculations. Rule of the thumb. What's the rule of the thumb calculations? Rule of the thumb calculations is something that you can do by heart, without any calculators, without doing any by hand. Okay? A simple uh, conversion in your head. Okay? So we have thermal equilibrium. Oh, let's talk about thermal equilibrium, right? What's thermal equilibrium? I didn't document here. Thermal equilibrium. Two objects are in thermal equilibrium when they do not exchange thermal energy. Okay? And what does it mean? It also means that they are at the same temperature. They are at the same temperature. Two objects at the same temperature are in thermal equilibrium. In other words, two objects at the same temperature are in thermal equilibrium. And They do not exchange thermal energy. Okay, so that's what you gotta know. Those are conceptual ideas. And what else you have to know? Okay, thermal expansion of solids and liquids. Oh, by the way, just what we see right in here is an experimental result. Okay. What you see right in here is an experimental result. It's also considered a law of physics. It's also a law of thermodynamics. The fact that 0 Kelvin is the lowest temperature you ever see in physics, is a law of physics. And how do we find that out? We know that, from experiments. From experiments using gas thermometers. Okay? Using gas thermometers. Let me see if I have a slide here. Oh yeah, here you go. Gas thermometers, right in here. There are a special type of thermometer that use gases. And how do we know that? Okay, from the law of gases. From the equation law, we know that if you warm up a gas, the gas is going to expand. If we cool it down, it's going to contract. Okay. We also know that the pressure can change in the container. If we warm up the gas and the volume doesn't expand, the pressure is going to increase. And there are ways to measure pressure. We measure pressure in the same way that we measure weight. Isn't that nice? Okay? You can use a scale, a slightly modified scale, to measure pressure. It's possible to do that. I didn't cover that here, but just believe that, okay? And remember, because pressure is a type of force, right? And a scale measure a force, which is a weight. Then we can use a scale to measure pressure as well, but it gotta be a more, a slightly modified scale to measure the pressure. What we find out that there is a relationship between pressure and temperature. Okay, and when we perform experiments with those gas thermometers, containers with a given gas, it can be different gases. I put here, I illustrated here, oh gosh, three different gases: nitrogen, oxygen, and another unknown gas. When we perform experiments at different temperatures, okay, we get, let's say, one gas at temperature of 100 degrees C, has this much pressure, the nitrogen gas. Another gas at 100 degrees C has also this pressure here. And this third gas, we're going to have a different pressure. Because they are different gases, they are going to behave differently in the container, and they are going to provide different pressures. Okay? Now, when you keep on, just like we do in the lab, right? Just like we keep on collecting data under different circumstances. Here, what we are doing, we are collecting data under different temperatures. Here, I have only 3 data points at 3 different temperatures for 3 different gases. What scientists find out? Nobody knows that's why, but we know that happens. Okay, we find out that the curve of the pressure is linear. Okay, for all those gases, the slope, their slope is different. Okay, however, their point of intersection here at the temperature axis ends up being the same. That's what we find, no matter what gas you use. What that would correspond to? That would correspond to a pressure of 0. Make sense? A gas at 0 pressure has ultimate lowest possible temperature. Has the gas at 0 pressure has the absolute 0 temperature. Okay, that's what it means. No substance can have a negative pressure. Okay, so no gas can have a negative pressure. That's why we stop right in here. That's why the temperature doesn't go any lower than 0 kelvins, because you cannot have a negative pressure of a gas inside a container. Okay, so that's how scientists discovered this absolute zero by performing experiments with different gases. Okay, that's now what else you have to know? You have to know about thermal expansion. Okay, what we do know about thermal expansion? Let me here we go.
Is we're in a vacuum. Does that mean it's zero pressure? And does that mean it's very cold?
Not necessarily cold. Okay, it depends if you have a source of heat in the vacuum. Like for instance, if you go to low the Earth's orbit with this vacuum, right?
Yeah.
On the side that the sun is heating, it's like 150 degrees C, I believe. Okay,
Yeah.
but on the shade of the Earth is sub-zero temperature.
Oh.
Okay, so just because you're in the vacuum doesn't mean that you're going to be at 0 Kelvin. Okay,
Oh.
it depends on you if you have a source of energy, a source of heat. Like the case is the sun. The sun is a source of heat. Okay, so okay, now let's talk about thermal expansion. Let me get the exact temperature. You can look at that in the internet. Let me see if I can find that for you. I believe it's 150 degrees C in the sunshine, in the sun, in the sun there in the space. Okay, temperature of what's going on here? Let's see. Temperature at low Earth orbit. Let's put it this way. Temperature at low Earth orbit. Huh. Nope. Temperature at low. Man, this computer is so slow. Earth orbit. Go. Temperatures of outer space around the Earth. Okay. What's the temperature outside the ISS? Depends whether it's in the sunshine or is in the whether it's in the shade. 250 degrees Fahrenheit, which is close to 150. Okay, 120 C. I said 150, right? But it's 100, 250 minus 250 Fahrenheit is minus 150 in the shade. Okay?
So do they have like really good air conditioning in there?
There? Oh, yeah. Uh-huh.
Like the air conditioning in the ISS?
Oh, yeah, yeah. They have to have something like that, yeah.
Oh.
And they also have to have a good heating system, otherwise the astronauts are going to freeze to death, right?
Yeah.
They have to have a, yeah. And they have to have other things too. They have to have protection against radiation, which is the things that generate heat. And you gotta be careful too because human body generates heat, right? Laptop computer that they bring there, they take there, they generate heat. So they have to find a way to take care of that heat, right? So the space station, when the Apollo 13 astronauts went to the moon, did you watch the movie Apollo 13? No, you gotta watch that movie, okay? They they have a failure. They have a major malfunction. They call it. It was a real major. Those astronauts they could have died if they had an explosion during the trip to the moon. It was a design fault of the spacecraft. There was an explosion, and they lost electricity. They lost a bunch of things, and they have to conserve energy to save the astronauts. They even ended up aborting the moon landing because of that. They were going to land on the moon. They had to abort the moon landing. And because they have to conserve energy, it became freezing inside the lunar module for the astronauts. And then when they returned to Earth, they were dehydrated. They were really in bad shape because you have to save energy, otherwise the astronauts are gonna. They have to reroute energy to the life support system of the astronauts, right? They have to do that. So
it's called the Man on the Moon.
Mhm.
Yeah, there's another one too.
Yeah.
It shows like from how NASA's statue started, and then he started building from all the way to the top.
Okay. And do they talk about the Apollo 13 there?
Yeah.
They do, right? Yeah.
Did Apollo 13 get struck by a lightning bolt?
No. That's a good question. I think so. Let me check. I read about that too. I do not know if it was Apollo 13, but Apollo Saturn rocket, right? Struck by lightning. Struck by lightning. I do not know if it was Apollo 13. Maybe it was, right? That flight was so. They had so much bad luck, right? Struck by lightning bolt. Yeah, I think I heard about that. Saturn V lightning strike. That was the rocket that took the man to the moon. Okay. 1960 lightning struck the Saturn V. 36 seconds after launch. As a result, many temporary effects was noted in both, but they don't say which. It was Apollo 12, not 13. Apollo 12. Twice. Twice. They say that it was struck by lightning twice. Uh-huh. Apollo 12. Yeah, that's right. Apollo 12. But they were able to land on the moon. Einstein almost killed the Apollo 12. Almost killed Apollo 12 mission. Yeah. Yes. Okay. So that's going back here, right? Thermal expansion. Okay. What you have to know about thermal expansion? No. Most. When I mean most substances expand when their temperature increases. And their temperature increases. Most substances. I'm going to underline here. Most. There are except. Oh gosh, what's going on here? This one here. Yeah. Most substances. There are exceptions. Okay. But most substances behave this way. There are exceptions. And water is one special exception. Okay, at certain temperatures, water doesn't expand as temperature increases. Water contracts in volume. That's why ice cubes float. Have you thought about that? A solid material in general has a higher density than the liquid material, than its liquid counterpart, right? But not with water. With water within 0 and 4 degrees C, the ice has a lower, the solid water has a lower density than the liquid water. That's why ice cubes float. That's the odd behavior of water. There's a very odd behavior. Very few substances behave like that. Okay, and that's good that water behaves this way. It's because of this behavior that we are here today. Okay, if water didn't behave this way, maybe we wouldn't be talking here. There are exceptions, but so what does it mean? Okay, we have, for instance, a bar. We increase its temperature, the bar is going to expand. It's going to become longer. That's how mercury thermometers work. Okay, temperature increase, the column of mercury increases as well. Okay, expansion of mercury, and alcohol too. There are alcohol thermometers out there. Water wouldn't be a good candidate to measure temperature in the region 0 to 4 degrees. Okay? Because instead of expanding, it would contract. Water wouldn't be a good candidate for a thermometer. And here you go. Here's a one-dimensional type of case. Here's a two-dimensional type of case. Okay, so if you have a two-dimensional plate, you increase the temperature, the lengths of the plate are going to increase in both directions by delta A. In the horizontal direction, delta B in the vertical direction. Okay? And the same thing happens to cubes, A, B, C. parallelepipes, not cubes, but parallelepipes. Okay, it is possible to mathematically model this type of expansion. Okay, there is something that we call oh boy, something we call the coefficient, even better, the linear coefficient of thermal expansion. Coefficient of thermal expansion. Okay. Different materials, different substances have different thermal expansion coefficient. Okay. And how do you model that? We model that in the following way. Okay, we do know that the higher the temperature change, the more expansion we end up getting. So it's going to be something like that. We go equation. Huh, what happened? I have to copy from somewhere. What's going on here? Okay, so here you go. Goes like that. So suppose that we have original lengths L naught at a known temperature T naught. Okay. And then we have a final length of the object L at temperature T. Okay. So we do know that the difference between L and L naught is linear with temperature within a small range of temperature. Okay. Just like we have for our Taylor, this thing works like the Taylor expansion series. Okay, so it's proportional to what? T minus T naught. It's proportional to this difference. In other words, delta L is proportional to delta T. The proportionality constant is the thermal expansion coefficient. Here we go. Alpha. Something like that. Okay. That's for a linear, for a long rod. I'm doing that for a long rod, 1D material. We start with the simplest possible situation, one-dimensional material. And one-dimensional material is what? Is something that has a length that 10 times its diameter, its cross-sectional size. Okay? Is this a one-dimensional object according to this definition? Is this a one-dimensional object according to this definition? No, right? This one has a thickness 1, 2 inches, 1, 2, 3, 4 inches, 1, 2, 3, 4, 5, 6, 7 inches. No, 7 is not 10 times 4, right? 7 is not 10 times True. Okay. What about this cable here? Can it be considered a one-dimensional object?
Yeah.
It can, right?
Yeah.
You measure its diameter, and its length is more than 10 times the diameter. Okay, that's a good way of defining whether an object is one-dimensional or not. Okay, another way of defining is this piece of paper a one-dimensional object? Huh? Is this piece of paper a one-dimensional object? Think about that. You gotta see if this length here is 10 times this width. Is it 10 times this width? No, right? Okay, so it's not a one-dimensional object. But now we're gonna go to another step, the next step. Now I'm gonna ask you, can I consider this piece of paper as two-dimensional object? Okay. Yeah. Now the next step is how do you define a two-dimensional object? Okay. A two-dimensional object is an object that has a thickness that's 10 times smaller than the shortest length, let's say. Okay? So it has a very small thickness, right? So yeah, it's considered a two-dimensional object. It's not a one-dimensional object, but definitely a two-dimensional object, right? That's how we. That's a very good definition, okay? And we're going to use those definitions here in those formulas that we're gonna get. Here you go. The alpha that you see here has. Let's take a look at its unit. Let me see if I have a table here for you to see. You have a table like that in your book. Let's see here. Alpha. Yeah. Yeah. Okay. Yeah. So it's proportional to that, but it's proportional to something else today I didn't write. Okay. It is also proportional. Here you go to L naught times delta t. Okay. So the equality becomes what? Alpha L naught delta t. Okay. The larger the initial length, the more expansion you're gonna get. The larger the change in the temperature you get, the more expansion you're gonna get. Okay? Can you remember that? In because of that, alpha has a units of what? The units of alpha is no units of alpha is going to be 1 divided by Kelvin. Okay. This guy has units of meter. This one has units of meter. This one has units of temperature. Consequently, the coefficient of thermal expansion has units of inverse of temperature. Okay, if an object expands, you go. If an object expands with temperature, okay, its coefficient of thermal expansion is positive. It's positive. If an object contracts with temperature, and like I said, there are objects that do that, substances that do that, not objects. Let's see, if a substance, okay, expands its coefficient thermal, if a substance contracts, substance contracts, this coefficient of thermal expansion is negative. Like I said, there are objects with negative thermal expansion coefficient. But they're oddballs. They're not the rule, they are the exception. Okay, so now we can predict what's going to be the length of a rod if we heat it up to a given temperature. This is going to be L plus, no, wait a minute, L naught plus, like that. Okay. Think of that as a Taylor series expansion. Taylor series expansion in temperature. That's how you have to think of that. Okay, 1 plus alpha, alpha delta T. Delta T, like that. So what's that? Again, remember, think of that as a Taylor series expansion up to a second order. Okay? The length is a function of temperature. Okay, what we have here? We have the zero order term here. The length at the initial temperature T naught. Okay? And then we have the first order term, that includes this coefficient of thermal expansion, the original length, and delta T, right? Just remember a function f, right? How can we write down a function f? A function f can be written down in terms of a Taylor series expansion as x calculated at x naught plus what? The derivative of f with respect to x, right? Calculated at x naught. Remember that? And what else we have? We have x minus x naught, right? X minus x naught. And if you want to go any further to our second order term, what we get? I gotta put a. It's so small. I need to learn the keystroke for this. What I want for this symbol that I want to do. Right parentheses only. It must be this one. This one. No, no. Okay, must be this one, I guess. Yeah, that's the one. And then what's gonna be? Do you remember that? We're going to have 1 divided by 2 factorial, right? Second derivative of f at x naught and then we get x minus x naught squared, and so on. 1, 2, 3. That's what we have here. That's exactly what we have here. Okay. The difference that I didn't go to the second order term. Fx naught is L naught, which is actually the L calculated at the initial temperature T naught. Alpha L naught is my first derivative calculated at the initial temperature T naught. Delta T is exactly T minus T naught, which corresponds to x minus x naught. Okay? And if you're dealing with larger ranges of temperature, then just going to the first order term is not enough to get a good estimate of the length. Then you have to go for the second order term, and so on. Okay? So what happens when we use that for two-dimensional objects? What happens when we use the above for 2 and 3-dimensional objects? Okay. Okay, so you gotta apply 2D. We have an area. Area is gonna be what? Area is going to be A times B, right? Let's say A naught, the initial area at temperature T naught is gonna be A times B. Then we apply a temperature. You go to a higher temperature, and we're gonna have a new value for the area. And the new area for the area, if the temperature changes is small enough, is going to be A plus delta A. And one side is going to increase by delta A, right? The other side is also going to increase, not by delta A, but by delta B. Can you picture that? Okay. And then we go ahead, expand this equation, right? Remember, this is the area at the initial temperature T naught. We increase or decrease the temperature to T, and the area is going to either increase or decrease by an amount delta. Each length is going to increase or decrease by amount delta A and delta B, right? We expand this relationship here. It's very simple, right? It's just the regular algebra. We're going to get AB. We're going to get A delta B. Let me see how I'm going to do that. I'm going to do like that. Here we go. AB. Here we go. I'm going to do like that. Better. And then like that. Right? Distributive property. And now we can go the next step. So that's what we have. Okay, so then we come up with an approximation, important approximation. Remember, delta A and delta B are much smaller compared to A and B, right? So when we multiply delta A with delta B, this term here is going to be far smaller than the other terms here. Okay? And that's when we apply the approximation. Here we go. Approximation. Here we go. Is going to be something like that. Okay? So what we have here now is going to be the first term, the original area, plus something else that I call a delta area. Okay? Something else that I call a delta area. Right in here. But we can go another step, a better step. Here you go. Let me do that. Before you go to that, you know, I will do something like that. Here you go. This one is A naught, right? We got A naught already there. This delta B is gonna be what? This delta B is gonna be exactly what I have right in here, right? Make sense? But instead of L naught, I'm just gonna put B, which is the initial length. Don't forget this guy here is alpha. This guy here is alpha, right? This guy here is A. And we get a similar result for delta A. But instead of L naught, it's going to be A. I'm going to rearrange my delta T. I'm going to put it here. Okay, I'm going to rearrange my alpha. Let's see how I'm going to do that. Yeah, I'm going to put my alpha in front of the A. Okay, and now you can see that I have my original area here again, right? What I call delta A is in reality, let me here write that, is in reality, oh, let me see how I'm going to do it. Oh, here you go. Look what we have. This term here is equal to this term, right? So you're going to have a 2 here. See that? Let's go another step. And then 2 alpha A naught. Okay? So this term here, just initially, I named it delta A. But it's better to keep this way. Alpha is in general a very small value. Let me give you an example here. Coefficient of thermal expansion. See, 10 to minus 6. Take a look here. Within a certain range of temperatures, for aluminum and steel, alpha is in the order of 10 to minus 6. Okay, so let's go. We're gonna finish it very soon. I want you to see how those formulas progress for the lengths is something like that. For the area, it is an approximation, yes, but it's a very good approximation. You know, it's gonna be something like that. Okay. 1 plus 2 alpha delta t. 2 alpha delta t. So you have alpha and 2 alpha. This 2 alpha we call the coefficient of surface expansion, and we give it a name, is a beta. Okay? And then we can do the same for the 3D case. Here you go. I'm just gonna copy that and paste here. For the 3D case is we have our V naught is equal to ABC. We have our final volume. Change it here. Here you go. 3D is gonna be A plus delta A, B plus delta B, C plus delta C. Like that. Okay, and I'm going to apply the distributive property. Right? Apply the distributive property here, apply the distributive property here. Right? There we go. Then what we're gonna get, we are going to go, apply that here and here. Right? And then we have let's see, delta A. I'm going to, no, we keep it, distribute C plus delta C. Here you go, like that. I made a mistake here. Good. Okay, next. Well, eventually, you know, I'm not gonna do all the calculations. Eventually, what you're gonna get, you know, if you're following what's happening here, the volume, you know, you're going to have something like that. ABC, okay, and it's gonna be 3 alpha ABC delta T. Okay? So what you get? You get the initial volume times 3 alpha, the initial volume, delta T. Okay, so that's how the progression goes. This 3 alpha, we give it a name. We call the coefficient of thermal coefficient of volumetric expansion. Okay, and we give it a name gamma. Here you go. That's how the progression goes. Do we have anything else? Okay. Yeah, that's 5:55 now. Let me take attendance and then we go for a break. Any questions? I'm gonna pause here. Don't forget to remind me to. Okay, here you go. So, the last thing, right? Oh, and by the way, now we have a new basic quantity, which is the number of moles of a gas, right? So let's go back to our notes here. New basic quantity. New basic quantity. New basic quantity. Number quantity of a substance, and the unit is the moles, right? So now we have length, mass, time, temperature, and moles. And in physics 38, we are going to see electric charge. Okay, 1, 2, 3, 4, 5. With this one is going to be 6. Okay, and there is an important relationship that you have to know. I want you to work some problems there so you get familiar with it. That relates the pressure, the volume, and the temperature that the gas is subject are given. Ideal gas, by the way, this thing applies only to ideal gas. nRT. N is a constant, a thermodynamic constant. R, right? R is a thermodynamic constant, just like the big G in the universal law of gravitation. Here you go. That's what's the value. Here you go. Universal law, universal gas constant given by that. Okay. So you can solve some examples. For instance, I did an example right in here. Ideal gas inside a rigid container, so the gas can be kept at constant volume. We double the temperature of this gas. What happens to the pressure that the gas exerts on the walls of the container? Okay, so here we go. No gas is leaking. Because no gas is leaking, PV divided by T is going to be equal to NR. Okay, so here you go. Here you go. This one here is going to be constant, right? And the volume too, if you put the volume in there. So PV divided by T is going to be a constant. P, initial V, initial T is going to be equal to final P, final V, final T. Okay? The temperature was doubled. And I am putting T here. Initial pressure, initial volume. The volume didn't change. Okay, temperature is going to cancel out. And then what happens to the pressure? The pressure doubles. You increase the temperature, the pressure is going to you increase the temperature by twice the value, and the pressure is going to increase by twice as much. What about another example here? We keep this is an isothermal process because the temperature is the same. The other one was an isovolumetric process. We cut the volume of the gas in half. Okay, cutting the volume of the gas in half doesn't mean that it's going to have less molecules there. No, the number of molecules remains the same. Okay, it's just the volume. the gases, can expand and contract, right? While keeping the same mass and the same number of particles. What happens to the pressure? Okay, cut the volume in half. You have the same gas compressed in a smaller volume, so the pressure should increase, right? And that's what happens. The pressure is twice as the original one, the initial one. Okay? So we can stop here. Unfortunately, we cannot go into chapter 20, but I'll let you study on your own. The final is going to include only up to chapter 19. Okay? Thank you for being here, and the exam starts 7 o'clock. Let me know if you have any problems. You can send me an email to my personal email address, and I'll be monitoring it in the next 24 hours. I see you on Thursday, right?
Wait, Thursday or wait a minute? Do we have class Thursday?
We are gonna have a final exam on Thursday.
Oh,
A final. Don't forget, final exam. You have to be what 5:30 to 7:30, right? There won't be any 24-hour window in the final exam. You have to be there 5:30 to 7:30. I'm gonna make it your window there. Okay. Again, yeah.
so the final exam is on campus or?
Yeah, on campus as well.
Okay.
On campus as well. Yeah, final exam. I'll send you an email and you're gonna get it. Okay. Any more questions? Okay, so thank you again and hope to see you next semester for Physics 38.
Professor.
Yeah.